All right, Mom, it's Sunday. I don't have a story, but perhaps, I don't know, an observation or a lesson anyway, we have a wall at the job, which will remain nameless. Everyone knows what job it is. That is in failure. It is a CMU, a concrete, cement block wall, 10 foot tall, which is fully grouted. And it has a rebar, or it has rebar in the very center. It's a 12-inch CMU, and the rebar is in the center. And the engineer who was helping us, who I'm just intrigued with, very intelligent, was explaining to me and the superintendent and the field supervisor that the rebar could not be in the center of the CMU, which just seems counterintuitive. And so it's hard to describe. Well, let me do this. So I tried to draw a picture of a CMU wall. One side of the 10-foot CMU wall is loaded up with gravel and soil, putting pressure on the wall. The current position of the rebar is in the center of the wall. It goes down to the footing and supposedly hooks onto another rebar, which I doubt actually happens. But what is occurring is the soil pressure, and eventually, if I'm using the correct term, the hydrostatic pressure of the water, and is pushing on this wall and could cause it to fail, which the rebar, in my estimation, is intended to help prevent. Now, what the engineer at the time was trying to explain to me and the other guys, I didn't quite get my head around it. And it's sort of, I love going to these meetings now because it's less about me trying to show what's wrong or what I believe is wrong, and more about me learning the solutions, not only with the structure and the framing, but other subs as well. And this one in particular intrigued me. And I may not have my head around it still, but I have a theory. So he was telling me, and he showed me these charts and tables, and my brain just explodes when I start seeing mathematical formulas and charts and all that crap. But there was an equation and a code that said on a 12-inch CMU block with a particular height and a certain amount of soil pressure and load, that rebar had to be 8.7 some inches or whatever eccentric of center, meaning opposite of the soil pressure. So the rebar not center, but toward the side of the wall that did not have pressure, that was in tension. So, as I said, I didn't really, I'm kind of nodding my head, semi-comprehending, but more or less pretending I know what the hell he's saying. But, a little bit later on, I got to thinking about what was going on and why that was. And I may be wrong, but as I said, I have a theory. And it's, of course, as I always do, base everything off my primitive technology and archery and whatnot. So my theory was based on the construction of a bow. And if you take the cross section of a bow, kind of represented as a CMU wall, the belly of the bow is in compression. The back of the bow is in tension. Belly in compression, back in tension. Right, this minuscule invisible line in the dead center of that bow limb is a neutral plane where there is neither compression or tension. It's completely neutral. The reason this potentially is important, especially in bow building, is some woods are better than other with certain characteristics. For example, a cedar bow is very good in compression, very strong in compression, not very good in tension. That being said, you have to design the bow accordingly to account for its failings in tension and to take advantage of its compressive strength. A hickory bow is super strong in tension, not that great in compression. Again, you have to design accordingly. An Osage bow, which is of course my favorite wood, is equally or close to equally strong in tension and compression. So when you have a bow that's lacking a particular characteristic, let's say it's weak in tension, you can apply a layer of sinew. All these backstrap tendons of sinew, that's processed sinew, which I point out because, well, let me get back to that. So you take, now this bow is in reverse, it's not strung. Get in there. Come on. All right, so this is not the best example in the world, but this is a hickory bow, which is already great in tension. This is the back of the bow, which means this will be the side that is in tension. But this is the wood I had, and I wanted to make a new design, which was a completely super reflexed, as you can tell. The tips point toward the target, unstrung, which will help store more energy. Then I added layers upon layers of sinew to the back of the bow. One, to help hold its reflex. Two, to give it a faster recovery and a faster trajectory, arrow feet per second. But one of the things that happens when you add a layer of sinew is inadvertently, because you're making that bow limb thicker, you are actually moving the neutral plane ever so slightly. If this had been perhaps Pacific yew or cedar or some other bow that's great in compression and not in tension, that would be advantageous, because when you move that neutral plane, you are making more wood available to do what it does best, which is compressive strength. And the sinew takes care of the tension. The tensile strength, the modules of elasticity, all that scientific shit, it just basically keeps the back of the bow from breaking. So I've got a flat hickory bow here, hickory self bow. I don't know if you can see. You see that little crack with those little dots? That is a compression failure, and that happened while I was tillering. I didn't take my time. I overstressed the bow in one spot, didn't have the tiller right, and a compression fracture occurred. Now, I tried to alleviate it by punching those little holes on each side of the fracture to where the stresses will go in that hole, and then I retillered the bow. But hickory will very rarely fail because it is so great in tension. I mean, I've had hickory bows with compression fractures all the way across their belly and still send an arrow 170 feet per second. This is the Osage bow with the rawhide backing. And as I said, the Osage bow is great in compression and tension. And really, the rawhide backing was more for decoration and protection of the back more than anything. But that bow is 45 pounds at 27 inches, so that'll just about kill anything on North America. And it has a slight reflex, which is good. I'm getting off track. My point was, I got to thinking about why that rebar had to be eccentrically placed in the CMU. And in my mind, if I pretend that piece of rebar is a sinew backing, that would make sense. You're moving the backing toward the area of tension, therefore allowing more of what concrete and CMUs do best, which is compression. They're weak in tension, damn near worthless in tension. But in compression, they're very strong. So having the rebar in the center only allowed, say, 50% of the CMU and a grout to do their job. But placing it eccentrically toward the tension side allows perhaps 65 to 75% of the CMU to do what it does best in compression. Even though, with regards to a bow, the sinew is on the very exterior skin of the bow, the back. I believe in principle, in theory, in my mind, that is what's going on. That's why that rebar has to be placed toward the tension side, to give the tension side more strength of the steel, the tensile strength in the steel, and give the compressive side more ability, I can't think of it, to do what it does, to act in compression. But in the same scenario, the same wall, the same job, the same, what did I just do? Regardless of where the rebar was placed, even if it was placed correctly, it has been found to still be in failure. And ironically enough, the solution is carbon fiber, which, to my estimation, even though I have never dealt with, I've seen videos, but I've never personally dealt with it. Carbon fiber in my mind is nothing but modern sinew. And what I believe they do is they put some sort of epoxy, it's probably some sort of agent, cleansing agent that they put on the CMU, then they epoxy it, and they lay the fiber mesh up the wall on the tension side. So as all that compression happens, instead of busting loose and breaking the grout joints and everything going to shit like it did at our house at Dakins Road, this carbon fiber reinforces the back of the wall like the back of a bow, keeps it from breaking. And I assume, well, I know the cool thing about sinew is if you use sinew like this and you use hide glue, which is the same, because it's high glue, it's the same product. It's the same animal product. It's like gelatin. Both the glue and the sinew dry at the same rate, which means as the sinew shrinks, it actually adds more strength and pulls the bow into more tension. I don't believe that's the case with carbon fiber. The carbon fiber mesh, it's probably a static mesh with a epoxy glue. So you put it on and there it is. But I could be totally wrong. That rebar may need to be eccentrically placed for some completely other reason. But I sort of feel like I'm onto something. You know, like I said, the CMU wall is the back of a bow, and you need to reinforce it in tension. It makes sense to put the reinforcement toward the tension side. Anyway, I'm going to try and show you this.